Hello. In this video, I'll be talking through my notes from section 13.1, which is about exploring periodic data. So this word might be new to you. Being periodic is about something repeating. And this is something we want to think about a little bit before we start doing more trig, because one of the contexts where we'll be applying trigonometry is in the case of a circle. And if you imagine a circle, what happens with a circle that doesn't happen, say, with a line, is if we keep moving around the circle, we wind up back to where we started. And anything we measure about the location on this circle, how tall we are, how far we are to the left or right, what angle we're pointing at, those patterns will just keep repeating as we spin around. So this notion of something that repeats is what we call periodic in a mathematical context. So we have some definitions here. So a periodic function is one that repeats output values. So if we keep going, if we think about the graph, as we keep following the graph from left to right, at some point it repeats exactly what it did before. One complete pattern is called a cycle, and then the period is the horizontal length of the cycle. Right? So basically it's how wide is each cycle if we look at it on the graph. And here we have an essential understanding. Right? Anything that's labeled as an essential understanding in your textbook, I'll probably put it in the notes. And just the idea here is that periodic behavior, even if we're not mathematically talking about a function, if we have behavior that we call periodic, that means it repeats over intervals of constant length. So you might think about, the school year in some sense is periodic, right? Every year we kind of go through the same pattern of school starts, go to class for a couple of months, have a break for Thanksgiving, break for winter break, etc. And every year that same pattern repeats. So we might refer to that as periodic behavior, even if we're not pinning down exactly what it is mathematically. So here we have a graph of a periodic function. So you'll notice, will highlight here, we have cycles that repeat. So suppose I start here at negative 15. Goes up and down back to the x-axis, then down like so. That's a full cycle, because if I switch to another color, what I'm highlighting here in green is exactly the same as what I've highlighted in pink. It's the same shape, it's the same size, it's at the same height. The only thing that's different is that it's been shifted to the right. And we're assuming that this keeps going. So the next one, even if we don't see all of it, follows the same shape and presumably does something like that. So I'm highlighting some of the cycles. Now in terms of the period measures how wide each cycle is. So I might notice very specifically here, this is at x equals negative 15. This is not labeled, but if you look at the grid, is at x equals negative 3. This one here is at x equals 9. And whether you subtract or count, we will notice that these are 12 units apart. So we would say that the period is equal to 12. And I got that from how I happened to do the cycles. Someone else might look at this, and instead of starting at x equals 0, they might pick another really distinguishable point, like the maximum. Someone might say, I think this is the easiest point on the graph to notice when it's at the very top. So we have a cycle, it goes all the way down kind of straight, and then back up kind of wiggly until it gets here. And then we have another cycle. So the shape of the cycle is a little bit different this time because we're changing our opinion as to what counts as the beginning or end. This goes on forever and ever and ever. So there really isn't a specific beginning and end. We kind of get to choose. If someone did it this way, they might say, oh, this is at x equals negative 11. This is at x equals 1. This is at x equals 13. And they're still 12 units apart. How far is it horizontally to get one whole cycle here? It's 12 units. So that's the thing about period. If you're counting it correctly, you're going to get the same period, even if two people disagree as to exactly how they're thinking about the cycles. So I've got a couple of notes here. So first one is what I just said. if a function is periodic, you should be able to identify its period in a few different ways by looking at corresponding points. Going back here, one person might think these top points are the most interesting things to compare. Someone else might look at those bottom points. Those are all 12 units away. I did an example where I kind of picked this point on the x-axis where it's kind of flat to over here. Now, make sure you're checking for when a full pattern repeats and not just a specific value. Let me erase what I did before and demonstrate that. What you don't want to do when you're measuring the period is just pay attention to a specific value of the function. Because suppose we did kind of what I did before, and I started there. So I could follow this graph. Right here, we're at y equals 0. If I follow the graph, here I get back to y equals 0. So if I'm not careful, I could say, oh, it's repeating. I used to have y equals 0 here. I now have y equals 0 again. That value has repeated. It's true that that value has repeated, but what has not repeated is the entire cycle. Because if I keep going over here, I'm getting stuff that is different from what I saw before. So don't just look at when a value or specific point repeats. Really make sure the entire pattern is repeating. And then also, sometimes we can vaguely say that a graph is repeating a pattern, but in order to call it periodic, it has to have exactly the same pattern with the same y values. So for example, if I had a wave and I said, oh, it goes up and down and up and down and up and down and up and down and up and down like this, right? It's going up and down and up and down, but you'll notice that kind of the widths as I do it are not the same. This up and down versus this up and down, they're not quite the same. This valley is wider than this valley. So even though there's a pattern of up and down, it's not fully periodic because it's not doing it exactly the same way. Or we might have something where it's doing it exactly the same way but changing heights, right? I could have a graph that goes down 2 units and up 1 unit, down 2 units and up 1 unit, down 2 units and up 1 unit. If I drew this perfectly, it might be that all of these things that I'm highlighting are exactly the same size and shape. But the problem is they're not at the same height. We need to have cycles that look exactly the same except for shifting them left and right. If we're also shifting them up and down, that doesn't count. Okay, now as the values of a function fluctuate over the course of a period, right, going back here, right, our values up and down and up and down and up and down with some fluctuation. Sometimes we want to pay attention to how much they fluctuate, right? Are we going up and down a lot or up and down a little bit? So a couple of things that we want to pay attention to when we're analyzing a periodic graph is what is its maximum value? This is basically the top y. What is the y coordinate at the absolute highest part of this graph? What is the minimum? Oh, a little typo there. There should be minimum. The minimum value is the bottom y. There's something called the midline. So the midline, it's called a line. It's a horizontal line that is exactly halfway between the minimum and maximum y values. Depending upon your graph, could look like it's in the middle. Sometimes there might not feel like symmetry, but make sure it's literally halfway between the top and bottom. And if you can't do that intuitively, you can take an average. Right? If your maximum, say, is at A and your minimum is at B, you can figure out what you have here by just averaging them. A plus B over 2, and that's your y coordinate. And then the amplitude is basically a measure of how much fluctuation they have. It's the vertical distance from the midline to either the maximum or minimum. So it's measuring how tall your cycle is, but it's not literally the total height. It's half the total height. So let's look at an example. Right here we have a very basic wave. So we will notice, we see a few different points where this occurs. It's periodic, so it keeps repeating. But what I will notice is that my maximum y value is at y equals 3. It keeps recurring, but I never get higher than 3. And then my minimum y value is negative 7. So maybe you can figure this out just by looking at the grid. If you want to be careful, you can take the average. So 3 plus negative 7 over 2 is negative 4 over 2, which is negative 2. So if I draw a horizontal line at y equals negative 2, I should be drawing a line where basically the graph is above that midline for half of it and below it for half of it. Right? In a case with a perfectly balanced wave, that'll be true. Sometimes it might look a little funky, but what we have here is a line that is definitely halfway between the top and the bottom. This is our midline. So their midline is a line with the equation y equals negative 2. It's the entire line. And now the amplitude is basically measuring compared to that midline. Right? The midline is like the average value. I'm going up and down and up and down and up and down, but the average value is y equals negative 2. Compared to that average value, how far up or down do I go? So on the graph, you could, draw it in. So here is a maximum. We could go straight up from the midline to the maximum. How far is that? This is at 3, this is at negative 2. Those are 5 units away. So our amplitude is equal to 5. And if you're doing this correctly, it should be the same in terms of how far down you go. If you find a minimum point, and then you find the point on the midline directly above that, this is at negative 2, this is at negative 7. Those are also 5 units apart. So our amplitude is equal to 5. The overall height of the graph from the very bottom to the very top is actually 10 full units. So be careful about this. The amplitude is not the total height. The amplitude is the vertical distance from the middle, from the midline, to the maximum or minimum. And then just a little comment here on applications, and you'll see more of this in homework problems, I think. One example of periodic graphs is a sound wave. If you were to use some sort of computer analysis of a sound wave, right, you might see some graph that does something like this, and then it's gonna repeat that pattern. Let's see if I can use Notability to cheat on this. Right, so you might get some sort of graph of your sound wave that looks like this. Right? It's just up and down with the same pattern. Right? Assuming we have some kind of sustained sound that lasts for more than a fraction of a second, if we analyze the actual energy behind that sound wave, we would see a periodic graph. And different components of this graph correspond to different things that we would hear. So the period of the wave corresponds to the pitch. If you have a shorter wave, right, a shorter wave like this versus a longer wave like this one will have a higher pitch. So the period of the wave is related to whether it sounds very high or very low. The amplitude corresponds to the volume. So if we have a wave that goes way up and way down, that would sound loud to us. If it's more like this, just a little bit up and a little bit loud, that would sound quiet to us. And then the other difference is the shape of the period affects what's called the timbre. The timbre is like the quality of a sound, right? If I have a person singing or a violin playing or a trumpet playing or an electric guitar playing, they could all be playing the same note or singing the same note with the same volume, but we know they all sound different. And what makes them sound different is actually the quality of this wave. A computerized tone has a very boring wave like this. If you think of just sort of the like a pure kind of just old school, like if you imagine like old video games, what those sounded like, while instruments and the human voice have very complex patterns like this. So this is just a quick understanding of how some of this is related to things you already know. If we have a periodic graph that represents a sound wave, different things we notice about that wave corresponds to different things that we would hear in that sound. All right, so that's basically it. And